Hi Chem 2, this is the second video for chapter 11. We're starting on page 11 of my notes. And the first thing that we want to take a look at is a very important graphic that you'll see in a lot of textbooks. And I have it drawn here by hand. And what it shows is what happens to the profile of the molecules in a sample as you add heat to them. Remember, when you're adding heat to a sample, basically you're increasing the kinetic energy of the molecules. So you're giving them more motion of all different kinds. So the three different kinds of motion that you can give any kind of particle is you can give it translational motion, which means that the particles are going to move quicker through space, right? So that's just physical movement like you would think of, like linearly, like moving here and moving there. And, or a better way to say it would be translational energy. The second type of energy that you can place inside of molecules is vibrational energy. The molecules are going to vibrate faster as you heat them up. So if you have a molecule like O2, and here's one oxygen and here's another oxygen, and the double bond between the two oxygens is between them, then what you do is at a low temperature they're going to be vibrating slower and stretching less, and then at a higher temperature they're going to be vibrating and stretching more, almost to the point where you heat them up so much that they can actually break the molecule and separate. So that's the second envelope of where you can store kinetic energy, and that's the vibrational modes. So we have translational, vibrational, and the third thing is molecules are always rotating on their own axis. So as you heat up a sample, you increase the amount of rotation and the speeds of those rotations. So the faster that the molecules rotate, the more kinetic energy it has. So as we heat up a sample, the energy starts to go into all three of those envelopes. So this graph shows on the x-axis the kinetic energy, the total kinetic energy of the system, right? Which corresponds to the temperature. It's not the same thing as the temperature, but as the kinetic energy rises, so does the temperature. They are directly proportional to one another. And the third thing that you could look at along this x-axis would be heat added. Remember, heat is when you transform or move molecular energy from one system to another. So you take a cold body and you put it next to a warm body. The warm body, the molecules inside are rotating, vibrating, and translating more. When they touch the colder body, those molecules interact with one another, and they start to get the cold body's molecules to move faster, rotate, translate, and vibrate faster. So that's how heat is transferred from one thing to another. Heat can only be transferred from an object when there's a temperature difference. Okay, so again, three things that you could equally put along the x-axis is this is the total kinetic energy of the sample, right? All the molecules in the sample. Let's say it's a sample of pure water. Okay, this is the absolute temperature of the sample, and the third thing that you could look at was the amount of heat that's added. So if you think of a beaker, it's filled up with that sample of water, and we put a Bunsen burner underneath it, and the Bunsen burner is heating up this sample. Right? As we add heat to the system from the flame, so heat's going to go up, the heat added is going to go up. The temperature is obviously going to go up, and the third thing that's going to go up, which is proportional to the temperature, is the average kinetic energy of the molecules. The kinetic energy of all of the molecules is going to go up. Okay, so let's take a look at this profile. On the y-axis is the number of molecules with a certain energy. So if I take a point over here and I look at this first lower temperature graphic, right, which looks like a statistical distribution curve, because it is, right? It's a little bit more sharp at a lower temperature than if I raise the temperature of the sample where it's drawn out. But in both cases, they have this typical bell-shaped curve. You see that? That's the higher temperature one. That's the lower temperature one. So let's start by talking about the lower temperature one. Okay? So the way you can look at this is that all of the molecules in the sample, their total energy is represented by the area under this low temperature curve, right? So if I was going to take all of this space under here, right, that would represent the total amount of energy that the samples have. So you see, at a lower temperature, most of the molecules, right, this is the number of molecules, right, and remember, all of them are covered underneath here, but any particular one, any particular molecule may have a temperature that's over here. Another one may be a little bit more energetic because it's moving faster. It may be over here. And then there may be a third one whose average energy is over here. But every molecule is someplace on this curve. Okay? There's none of them way out here beyond the curve, and there's none of them before it. They're all somewhere on here. Okay? So what does the peak of the mountain at low temperature represent? It represents the average or the typical kinetic energy of the molecules. So if we gave this a number here of, like, let's say a kinetic energy of 50 joules, then the average kinetic energy of the molecules would be 50 joules. Some would be less and some would be more. Okay? So at lower temperature, the distribution is tighter. Right? Most of them are centered around this average temperature. So what happens when you raise the temperature of our sample? So the water is in here, pure sample of water, and I raise the temperature. What am I doing to the sample? Well, the first thing that you'll see is that the area under the curve is the same because you still have the same number of molecules, right? There's got to be someplace underneath there. So this whole area should be equal to this area. This one is taller, but this one is wider, right? So that's the first thing. The second thing is the average kinetic energy. What is the top of this mountain? Now, don't look at this line right now, okay? The top of this mountain happens to coincide with close to it. Maybe it coincides right here, just a little bit to the left of it, okay? So that would be just a little bit to the left of this line over here would be the average kinetic energy of the molecules at higher temperature. So when you raise the temperature of the sample, you're increasing the average kinetic energy of the molecules. Of course, you're raising the temperature, the molecules are rotating, vibrating, and translating faster. Okay, next thing. Another thing that you notice is they spread out more, right? So they're not so tight around this central position. There's more variability, okay? All right, last thing. What is this fixed line that's in here? Okay? Well, this is the kinetic energy required for a gas molecule to escape. So, once I get the average kinetic energy of the molecules, okay, bring this graph by raising the temperature higher than this fixed line. If we went to a third temperature, the third one might look like this. Right? And then, over here, I'd say, wow, my average kinetic energy of the molecules is so high that the majority of the molecules under the highest of the three temperatures is much greater than the amount of energy it takes for the molecules to escape the liquid. Remember, there's intermolecular forces between the molecules that are holding the water down. How come the water doesn't just evaporate, right? How can you have a standing glass of water with the cover off? Well, that's because the forces between the molecules are stronger. So in a typical glass of liquid water at low temperature, only a few molecules, see these little ones under this curve here at the low temperature? Only these guys over here would have enough energy to escape. So the majority, 95% of them, are smashing into each other and don't have enough energy to escape. Okay? So at a low temperature, the amount of evaporation is very low. When you increase the temperature to our second temperature, though, the amount of molecules that have enough energy to escape is everything to the right-hand side of this line, all of this here. So to me, what percentage is this over the total bell curve? I would call this 40%. So 40% of the molecules are hitting into each other with enough energy to escape the liquid and go into the gas phase. Now, does every single one of them do that? The answer is no. 40% of them have enough energy, but we need two more things to happen. One is they have to be close to the surface. How can a molecule, right, we're not boiling yet, how can a molecule, even though it has a high energy over here, this particular one happens to be one of the ones on this right-hand side of the curve. If it's in the middle of the liquid and it has that high energy, it can't escape. In order to escape, you need to be close to the surface, right? And not only do you need to be close to the surface, you need to be oriented that your particular translation is going up and out, right? So evaporation is a surface phenomenon. This is before something boils. The amount of evaporation here would be much higher than it would be at the lower temperature, which makes sense because now, instead of 10% of the molecules having enough kinetic energy to escape, wow, 40% of the molecules have enough. That's not even 10%. Let's say this is 5%, and this is 40%, right? So that's why you see much more evaporation in a hot liquid, because a higher percentage of the molecules have enough energy to escape. Okay? So think about these graphs. Two things that you're responsible for is when you raise the temperature of a sample of a liquid, okay, any liquid, and especially a pure liquid, by heating it up, you increase the average kinetic energy of the molecules. You go from here to here, right? This has a higher kinetic energy than this, the top of the peak. The second thing that you do is you spread out the graph so that the variability, right, is much greater at a higher temperature. More of them are spread, the tail is longer, and this tail, the positive tail, is also longer. So this tail and this tail is longer. And the last thing is, this fixed amount of energy is the amount of energy that you need to escape the surface of the liquid. When your kinetic energy is greater than the amount of work needed to break the intermolecular forces between the water molecules. Remember, all the water molecules are holding each other together. When you have enough energy to do that, you can escape. And escape, then, last thing, is not certain, because yes, 40% of these guys have enough energy, but what's the problem? The only ones that can't escape from the bulk of the liquid, there's a gazillion molecules between here and here. They can only escape when they're at the surface, and the particular direction that they're moving in is up and out to break through that surface and get into the gas state. These are free gas molecules up here. Okay? If I am close to the surface and have enough energy, but I'm diving down, I'm not going to escape. Right? It's common sense. To escape, you need to be up and out. So let me erase this stuff, and we'll move on. But I love this graph. Okay? So you should study it from the textbook. We'll talk about it in class. There's much more beautiful versions of it than mine, but you need to learn it, okay? That idea, number of molecules versus kinetic energy, temperature in Kelvin, or heat. Okay, so let's talk about boiling. The difference between boiling and what we've been talking about so far of surface evaporation is boiling is not a surface phenomenon. Boiling takes place in the bulk of the liquid, okay? So what's special about boiling? The definition of the boiling point is when the vapor pressure of the liquid, right, the amount of molecules that are evaporating from the surface, is equal to the external pressure acting on the surface of the liquid. So here's my liquid. What's P external? Well, that depends on what the atmospheric pressure is. If I have an open beaker sitting on the bench in the lab, typically the external pressure is going to be 1 atmosphere of pressure, right? That's what we typically feel living in New Jersey. We have 1 atmosphere of air pressure pushing down on us, okay? If I was up in Colorado, this would be like 0.9. It would be lower, so things could boil easier. So what has to happen now in order for something to boil is that an imminent bubble can only form, right? Can only form when I can push out on the walls of this newly born bubble to the point that it can stabilize and stay open. You see, if this external pressure, the weight of the air pushing down on the liquid is so much, then a bubble can't even form at all. Because a bubble, folks, is not air inside. When water is boiling, inside those bubbles is water vapor. H2O gas is in there. It is not air. H2O gas is in the middle of the bubble. And the bubbles can only form, they can only hold out the walls of water, right? When the pressure within them, the vapor pressure, due to the force of the molecules, of the gaseous molecules against the wall of the bubble, is greater than the atmospheric pressure. That's why I can get substances to boil at different temperatures. That's why boiling point is very much a function of temperature. Water's typical normal boiling point is 100 degrees Celsius at 1 atmosphere of pressure. If I reduce this atmospheric pressure to 0.5 atmospheres, then there's much less force down on the top. Bubbles can form much easier, therefore they can form at a lower temperature. I can get water to boil at 40 degrees, at 50 degrees Celsius. By doing what? By lowering the pressure. So the pressure of the vapor inside the bubble is equal to the external pressure from the atmosphere. That's the definition of boiling. Boiling is not simply evaporation at the surface. That's still going on, right? That's individual little molecules coming up, one molecule at a time, and breaking through the surface. That's evaporation. How is evaporation tied to boiling? In order to form bubbles, you need to have the imminent vapor pressure inside the bubble equal to the atmospheric pressure. Okay, page 12. A liquid can boil at a lower temperature if the external pressure is lower. The normal boiling point of a liquid at 1 atmosphere of pressure, or the definition of normal boiling point, is the boiling point of a liquid at 1 atmosphere of pressure. The normal boiling point of water is 100 degrees Celsius. Okay? In a little while, we'll take a look at vapor pressure curves from the textbook and phase diagrams. Okay? But let me tell you about a specific spot that we're going to look at, or two things that we're going to look at from this page before I open up the textbook and show you. The first thing is called the triple point. The triple point on these phase diagrams that I'm going to show you is the point on the phase diagram representing the temperature and pressure at which 3 phases of a substance can coexist. That substance has a triple point. In other words, it is an equilibrium temperature and pressure. It is a temperature and pressure where the solid, liquid, and gas version of a particular material can all coexist, and you can move between all 3. We're not used to this. We're used to looking at the phase transitions 2 at a time, right? We tend to be fixated on water, where we watch the transition go from solid to a liquid, and then at a later temperature, from the liquid to the gas. But you can find on one of these phase diagrams that I'm going to show you a special spot where all 3, the solid, the liquid, and the gas, can coexist, even for something like water. You can do it for carbon dioxide, which the solid form we think of as dry ice. Liquid carbon dioxide is also very useful in industry. It's actually used as an organic dry cleaning fluid, so you're basically washing your clothes in liquid carbon dioxide. And how do you get to these unusual phases of carbon dioxide? You just have to get to the right temperature and pressure, and you can liquefy it and ultimately freeze it. Okay, so we'll talk about that. The second thing that we're going to talk about is the critical temperature. The critical temperature is the temperature above which the liquid state of a substance can no longer be formed regardless of the amount of pressure applied. So what that means is simply putting pressure on the liquid without also lowering the temperature won't be enough to change the phase from a gas to a liquid. So the critical point is the temperature above which only pressure that you can't just raise the pressure to liquefy something. So above the critical temperature, the liquid and the vapor phases are kind of indistinguishable. They're just fluid phases. You can't really tell. And this is usually at higher pressures and higher temperatures. There is no real boundary between the liquid and the gas. The line on these diagrams is going to go from a solid line where there's a definite boundary between the liquid and the gas to a dotted line, okay? Or it's basically just going to disappear off the map. Okay, so from that's finishing page 13. Let me backtrack, get the textbook, and show you vapor pressure curves and phase diagrams, okay? They are together. They make for great multiple choice questions. They're fun to work with. This is in chapter 11. Let me take a look at this one here. Okay, so this is a generic. I'm going to see if I can just autofocus. That's pretty good, right? Okay, so this is a generic phase diagram for a pure substance. In a couple of pages, I'm going to show you the phase diagram for pure water and also for carbon dioxide, so we'll get into specific situations. But the typical phase diagram tracks the pressure on the y-axis and the temperature on the x-axis. Now you can do these in Celsius or Kelvin, doesn't matter for temperature, and pressure you can do either in atmospheres or millimeters of mercury or torr. Most of the time we're looking about the general trends. We're not interested in the absolute number. Okay? So they typically have a Y shape, okay, like this. And this place where the point is, the point of the Y, you see the Y going on? Okay? That's the triple point. At that specific point, let me see if I autofocus this a little bit. Okay, a little better. Gotta move my computer out of here. How's that? Okay, so at that specific point, right, at that temperature and that pressure, the solid, the liquid, and the gas can all be in equilibrium with one another. That means you can have boiling, right, by making a subtly moving in this transition. So boiling is going from the liquid to the gas. So if you go across this way, right, you can have freezing, you can have sublimation, and you can also have deposition when you go this way. So you can have the direct changes. Okay, so that's the triple point. Okay, let's talk about normal phase transitions, which we think of at a constant pressure, so sticking at a particular pressure. Whenever we cross one of these lines from the green solid area to the yellow gas area, and these are always going to be set up where the solid is going to be the one that's at low temperature, which makes sense, and high pressure. The gas is going to be favored at higher temperature and higher and lower pressure. See down here? And then the liquid is going to be stuck in between the two. Okay? So we'll go back to this critical temperature up here, or critical point, when you can no longer tell the difference between the liquid and the gas, right? That's why this just kind of blends together between the blue and the yellow, right? All right, so since we're talking about it, we might as well talk about it. Above that temperature, just increasing the pressure. Now, what's increasing the pressure? Increasing the pressure is going up, right? So I can't, over here, I could liquefy the gas, not by changing the temperature, but by going straight up. If I go straight up, I can liquefy the gas. See? Pressure alone did it. What happens if I try that over here? If I try that over here, it's not going to work because the gas is indistinguishable from the liquid, right? So that's the last temperature where simply raising the pressure can liquefy a gas, right? You can always liquefy a gas by lowering the temperature, going down this way, right? That's making the transition that way. That'll always work. There's no place where you can't have that, okay? But above this point, just pressure isn't going to be enough to liquefy the gas. Okay? All right, so let's talk about this. Whenever I go directly from the solid state to the gas phase, right? Skip the liquid altogether. When is that going to happen? Low pressure and low temperature. That's called sublimation. This happens with water all the time. We call it frost. We see it in the wintertime, right? You have a pile of snow outside, and you come back the next day, and the pile of snow is getting smaller. How come the pile of snow is getting smaller when the snow never melted? I don't see any water around. The temperature never got above zero. Why is the pile of snow getting warmer? Well, one thing is the ice is kind of condensing it down to make it a smaller volume. But the other thing is the ice at the surface is evaporating and going straight into the gas phase. Okay? And then we form frost on our car windshields in the wintertime. It's not wet. We go out to my car windshield, and what do I see? Or on a blade of grass, I see this very, very thin white powder that forms on the edge of and easy to scrape off, right? Not the hard stuff like frozen rain. The easy to scrape off. Well, that's frost, right? The going directly from the gas state to the solid state. So we see this even with water. Okay? And then up here, this is what we typically expect. So for water, 1 atmosphere would be over here. 1 atmosphere of pressure would be over here, because we would go first from the solid to the liquid at 0 degrees, and then from the liquid to the gas at, so maybe we'd be a little over here, at 100 degrees. So let me move that down a little bit, because we would not be above the critical point. We would be down here. This would be 1 atmosphere for water. So if this is the water diagram, I'd go across. This would be 0 degrees Celsius, then keep on going across at the same temperature. This would be 100 degrees Celsius. Okay? So very important kinds of diagrams. They're called phase diagrams. Critical point, you're responsible for. Triple point, then you're responsible for this idea of what phase change is it when you go across this way, when you go across this way, and when you go across that way. Okay? Let's take a look at some specific examples. Sorry about that. All right, so this is let's see, make sure I get the right one. This is the phase diagram for liquid water. Okay, for water. And so you have the solid section, the liquid section, and the gas section at 1 atmosphere of pressure. Okay, I would cross over here. When does ice melt? It would melt exactly at 0 degrees. Then I go up. This would be 100 degrees Celsius. So in water, it's very highly exaggerated. The other thing that's interesting, first of all, there is a critical point for water. You get a supercritical fluid when you have water above 217 atmospheres of pressure, okay, and above 375 degrees C. Everything past that, you can't tell the difference between the liquid and the gas. Okay? The molecules are so, gas molecules have been squished so close together that they're indistinguishable from the liquid. Okay? The other special thing about water is very unusual. It is one of the only substances, if not the only substance, where this line in the V is going backwards and heading back in that direction. Even though it's very, very subtle, look at the difference with that one compared to the one that we just did. This is the typical kind of V, where it goes up this way, or I should say Y, and then separates out like that. See how both of these two lines are tilted to the right? Not the case with water. So it gives water this incredibly unusual property. What is that unusual property? The unusual property is that you can squeeze water, right? You can squeeze, by going to higher pressure, squeeze ice and get it to melt. Let me show you. Now, it's hard to see because this line is almost straight up, but everybody see it is bending backwards a little bit. So at a particular pressure around 0, if I raise the pressure, what's going to happen is I'm going to go from the solid state, I have to cheat a little bit, okay? Pretend that my line is straight and this is going back. I go directly from the solid state to the liquid state without raising the temperature, but by only doing what? By squeezing it. Now, this unusual property allows for ice skating and skiing and doing all sorts of really cool things in the winter, because by putting ice skates or skis on and having all of your weight on a small area, especially on an ice skate, you cause the ice underneath your blade. It goes into that tiny groove, the bottom of the skate blade, right? Here's the person's foot, right? Looking at it from the back. And you have all of that pressure on here, causes it to melt, and you create little droplets of water, like beads of water, inside or in between the skate blades. And that's what you're rolling on. You're almost roller skating on these tiny beads of ice. Same thing with skiing. If here's the ski, and the ski is against the snow, okay? So now let me make the person ski downhill. It's kind of weird for them to ski uphill. Okay, let's have them ski downhill. Okay, so here's your ski. You're putting weight on the ski. So underneath the ski, you're melting the snow, creating water, and that's what you're sliding down. It's like a slip and slide, really, for water. That's why even on a very cold day, you look down at your ice skates or you look down at your skis, and they're always wet, right? They have water accumulates around your boots because the pressure that you're putting on the snow is helping to melt the snow, or in this case, the ice for the ice skates. So this is a special property of water. Okay, when I show you carbon dioxide is not going to do that. It's not going to be tilted backwards like this. It's going to be tilted this way like you would expect, like all of the other substances. Okay, here's carbon dioxide. Up at the top, this is the phase diagram for carbon dioxide. Look how exaggerated this line is, the way it slides back that way. That's pretty cool. Okay, so here you're going from dry ice to liquid carbon dioxide, which again is very practical. It's an organic solvent, right? So you can clean your clothes by washing them. You don't even need to have soap. Okay, you can sort of wash them in liquid carbon dioxide, and the liquid carbon dioxide will help to remove or dissolve the dirt from your clothes and pull it into the liquid phase. And then you just take the clothes out of there, right, when they're still clean, and then you evaporate the carbon dioxide. It goes off, and reuse it again and take the dirt and throw it away. So it's a process that you can use, not the typical dry cleaner, but some organic dry cleaners use liquid carbon dioxide to clean your clothes. They use this special place right in here. Here's typical first of all, what is the triple point? At what temperature and pressure can carbon dioxide gas, liquid carbon dioxide gas, and dry ice all coexist? A little hard for you guys to read, but it's minus 56 degrees Celsius and 5 atmospheres of pressure. So not a lot of pressure. Okay, where do we live? We live up here at, down here at 1 atmosphere of pressure. So 1 atmosphere of pressure, cross the line. What do we usually see? Dry ice, sublime, and go directly into carbon dioxide. So you have a piece of dry ice, and you see the smoke coming off of it. We'll talk about that smoke that you see actually isn't the carbon dioxide, because the carbon dioxide is invisible, but it's a remnant of the fact that the carbon dioxide is coming off is so cold that it's making condensing water droplets around it. So if you had a completely dry area, you wouldn't even see the carbon dioxide evaporating. But what you see, the smoke coming off, is really water droplets from the air because of the cold carbon dioxide that's evaporating. Okay, so that's where we live. We live down here. Okay, what would I want to do to make liquid carbon dioxide at my organic dry cleaning company? I just need to raise the pressure of carbon dioxide over here. Okay, so at this temperature, 0 degrees, I just need to be at a higher pressure. Okay, excuse me, at a higher pressure. So raise the pressure, I can squeeze gaseous carbon dioxide into liquid carbon dioxide. This would be the sweet spot. Okay, you don't want to be up here because you'd be supercritical. You just want to be over here at liquid carbon dioxide. Okay, and critical point, 31 degrees Celsius, so it's not very warm at all. That's a normal temperature, but 73 atmospheres of pressure, so it's mostly pressure that you need to apply to get to this critical point. Okay, so those are the three great examples. Here's a general one. Here's water that you're responsible for. Here's carbon dioxide up at the top. Okay, I'm going to erase all this junk. Keep my textbook nice. Okay, get rid of this ski and ice skate. It's a very bad ice skate. All right, great. So that covers everything in terms of the idea of phase diagrams and triple point and critical point. The one thing I have to quickly go back to is vapor pressure curves, which was a couple of pages before that. Okay. So vapor pressure curves are related to the Clausius-Clapeyron equation. If you were to, instead of graphing the vapor pressure here and the temperature in Celsius, you were graphing the natural log of the vapor pressure versus 1 over the temperature, you would get our Clausius-Clapeyron types of curves that look like this. Remember, we did the ln of the vapor pressure versus 1 over temperature, and for all different pure substances, you got lines that went down like that. So this is a way of linearizing this kind of data. This is what's actually happening in the natural world. What you would expect when you raise the temperature of any pure liquid, so there are 4 examples here: ethylene glycol, water, ethyl alcohol, and diethyl ether. They are 4 pure liquids. Okay? Here's the temperature in Celsius. The vapor pressure at very low temperatures for all 4 of them is very low. How much is evaporating off of the surface? Okay? But as I raise the temperature, they all go up exponentially. Water is a great example. Look how exponential curve that is. Here's ethyl alcohol, which is regular drinking alcohol. This is diethyl ether, which is more volatile and flammable. And here's ethylene glycol, which is used as in antifreeze. It's the active ingredient in antifreeze to stop water from freezing and boiling. And here's ethylene glycol. So look, it moves up very slowly, but still isn't linear, right? It's not a straight line like this. It's still curved, right? So you want to straighten out the curve of something. You take the log of it, okay? And when you have something that is kind of going up like this, sometimes it helps to not graph the temperature or the Kelvin temperature, but 1 over the Kelvin temperature. And you'll do this to it, okay? But now let's take a look at this thing. So these are vapor pressure curves, okay? Now they're put on the same graph to make a point. The point is that we know this special place called the normal boiling point. The normal boiling point, remember, anything boils when the vapor pressure of the liquid equals atmospheric pressure. So this pressure along here, when the vapor pressure equals atmospheric pressure, when the vapor pressure is 1 atmosphere, the substance will not only have evaporation from the surface, but deep within the liquid, bubbles can form, and their density, since they're gas inside of a liquid, will rise to the top. So it's a great way to carry energetic molecules from deep within the surface up to the top, right? Because the gas is less dense than the liquid, so once the bubble forms, it's going to quickly rise to the top, and all of that gas is going to escape. All right, so here's our liquid. Okay, here's a bubble that starts to form. As it goes to the top, more and more gas molecules evaporate, and the bubble gets bigger. The other reason why the bubble gets big right before it's going to the top is you have less weight of the water, so there's less pressure pushing down. So the bubbles are going to start out small. They're growing for 2 reasons. One is more water is going to evaporate into the bubble, so they're going to go from the liquid phase into the gas phase. So that's going to stretch out the shape of the bubble and make the bubble bigger. And since the pressure is lower because you have less weight of the water on top, the bubbles are going to grow. When something's really roaring bubbles, when they hit the top can be huge, right? You think about right before you put the pasta in, right? The bubbles are enormous. Okay. And so ethylene glycol's normal boiling point at 1 atmosphere of pressure, it'll boil at 34.6 degrees. Ethyl alcohol boils at 78 at 1 atmosphere of pressure. We know water boils at 100. Sorry, this is a little hard to read. Oh, that's better. Okay, let me get closer. And ethylene glycol, doesn't even make it up to the gut, so you can't even get it to boil under on this graph. Okay. Right. I can get all of these liquids to boil at a lower temperature by lowering the external pressure. If I lower the external pressure to, instead of 760 torr, right, 760 torr or 760 millimeters of mercury make 1 atmospheric pressure. If I lower it to 400, I can get the ethylene glycol to boil way down here at about 15 degrees. I can get ethyl alcohol to boil at 60 instead of 73. And I can get water to boil at 80 degrees, right? Instead of, or maybe 82 degrees instead of 100. So that's the effect of lowering the external pressure, right? Boiling then again is when the vapor pressure of a substance is equal to the external pressure, the pressure of the air or gases on top of the liquid. Total pressure on top of the liquid. Good. Okay, let's do, I'm going to move this back a little bit, and we're going to finish up section 2, probably by going through just another, let's go through another 3, how about another 4 pages of notes, and then we'll take a break. Okay, so first thing is, what is actually going on inside the liquid? So these are properties of pure liquids. We're not talking about solutions yet. That's going to be in 2 chapters from now in chapter 13. So chapter 11 is just pure liquids. So you have 2 different kinds of forces that are occurring between the molecules. The first kinds of forces are called cohesive forces. Those are the forces that bind molecules together. So if you think about it, okay, let me get a little bit more color here so you can see it, right? I don't want to bleed through to my notes, but since this is graph paper, let me just take 2 sheets. So if I have one water molecule, and we know what water molecules look like, that's one water molecule, and then here's another water molecule in the liquid. All right, so they are distinct entities. Here's one water molecule and here's another water molecule. So the cohesive forces are the forces between the 2 molecules. Turns out that this hydrogen on this water molecule is attracted to this oxygen on the other water molecule, and that's the glue that holds them together. This is partially negative and this is partially positive. So this little small delta looks like a musical symbol. It means a part of a charge, right? So this is a part of a positive is attracted to part of a negative. These are forces of cohesion. Okay? Well, adhesion is the forces that bind the substance to a surface. So if this is glass over here and the water molecule is close to the glass is made out of molecules, and the glass molecules have different properties. So there's going to be forces between here and here. Those are called adhesion. That's why you get words like adhesive. Adhesive is a material like glue that you use to bind one material to another material. Those are forces of adhesion. Cohesion is the forces that hold one homogeneous material together. What holds water together? What holds liquid mercury together? Why don't the molecules just evaporate? Why do they stay down in a puddle? Those are because of the forces of cohesion. Okay? So within the forces of cohesion, there are going to be intramolecular forces and intermolecular forces. So let's first start out. I can go back to my picture here, as well as, actually I'll use the one that I have on the notes. It's probably nicer. So intramolecular forces are huge. Those are the forces that hold this hydrogen atom to this oxygen atom. We know that's a strong covalent bond. That's the sharing of 2 electrons between hydrogen and oxygen. So this guy here, the solid line, is the molecule inside one water molecule, and here's another one. These are enormously strong. They're 1,000 times stronger than these interactions, which we're just going to draw as dotted lines, between this water molecule here on the right and this water molecule on the left. So again, intermolecular forces are the forces between one molecule and its neighbor. Intramolecular forces are the forces within the molecule. So if you think about a family, this would be having a fight inside your family, and this would be you guys fighting with your neighbors. Okay, so the fights inside the family are much more intense, right, than the fights between you and your neighbor. Those are just like giving dirty looks and stuff like that, right? You know, you don't really have the guts to actually fight with your neighbors, but boy, come home, you do a lot of crazy stuff. All right, so you see the difference? Intramolecular within a molecule, intermolecular between molecules. All right, so you're going to be responsible. This chapter is going to focus on the intermolecular forces, the forces between molecules. And these are the kinds that you're going to be responsible for. First one is called ion dipole. Okay, those are the forces between an ion, which is something that's a cation with a positive charge, or an anion with a negative charge, and a molecule that has 2 sides, that's lopsided. So a molecule with a dipole would be a molecule where one side is partly negative and the other side is partly positive. So there are many molecules that have this distribution of charge where it's lopsided. The charges are not distributed equally. One side is negative and then the other side is positive. I'll give you an example. Example of that would be HCl. That molecule, the chlorine is the negative side and the hydrogen is the positive side. This is a dipole molecule. It has 2 poles. Okay? Very different than something like a helium atom, which is super symmetrical and its charge distribution is evenly distributed. It doesn't have sides to it. It's not like a big Italian bread where one side is a big French bread, right? One side is negative and the other side is positive. Okay? So if one of these guys interacted with a positive ion, this kind of forces between it would be called an ion dipole. Here's the ion, here's the dipole. Second kind are dipole-dipole. Well, if you've got one of these negative positives, it's kind of like a little magnet. If it's in a solution with millions of molecules, where's the one underneath it going to look like? Well, it's probably going to line up where this guy's negative interacts with that one's positive because opposites attract. If you took a bunch of magnets and you just small magnets and you just drop them down into a pile, they would rearrange a little bit, right? The best that they could to get in the best, lowest energy alignment. Well, the solution does the same thing. The molecules, although they can move and slide past one another in the liquid, they do feel each other strongly. So what would this interaction be called? Dipole-dipole. Okay? The third one is the weakest kind. Okay? These are called van der Waals forces or London dispersion forces. These are the forces that hold, the very weak forces that hold molecules together that aren't polar, that don't have a positive and a negative side. Something's got to hold them together. Helium, yes, you have to go to very, very low temperatures to get it to liquefy. But there is a point at which the helium molecules feel each other and like each other enough that they'll stay down. They don't go into the liquid. And you have to go down to 4 degrees Kelvin in order for this to happen. So very, very cold temperatures. You have to remove most of the heat, because if there's enough heat energy around, you'll give them enough kinetic energy that they can shake loose and go into the gas phase. But even something like helium there's got to be something that holds it together. So in the absence of everything else, when you have symmetric molecules that don't have poles, and you can still liquefy them, what holds those together? They're called London dispersion forces. And the last kind is an exaggerated version of dipole-dipole, special situation of dipole-dipole, and those are called hydrogen bonding. Hydrogen bonding is a special situation that's probably 10 to 100 times stronger than the dipole-dipole, at least definitely 10 times stronger. And there are intermolecular forces that substances like water have whenever hydrogen is covalently bound to either a oxygen, a nitrogen, or fluorine. In those special situations, the dipole-dipole situation is exaggerated to the point that we call them hydrogen bonds. So I'll show you those examples. Okay, so special case. Okay, let's look at some of the properties that are affected by these kinds of forces. Okay, so the first one is called viscosity, when something is very viscous. So my favorite example of viscosity is honey, right? Honey is among the most viscous, or syrup. It's one of the most viscous substances that we know of. So the definition of viscosity is the resistance of liquids to flow past one another. The greater the viscosity, the slower the liquid flows. Okay? So the ease at which, and what's causing things to be very viscous? It's the ease at which molecules slide past one another. So honey has sugar molecules in it, right? And sugar molecules of all different kinds, right? Fructose, sucrose, glucose, all of these different sugars. What do they have? They are long chain molecules, and they have tons of hydroxides coming off of them all over the place. There's these OH bonds all over the place in these sugars. That's what makes them a sugar. So when these kinds of molecules try to slide past one another, and here's another one with all these OHs, there's a lot of interaction between the oxygen on one and the hydrogen on the other, and they just can't get past one another. It's like Velcro. They can't slide past one another, and that's what makes them very viscous. Certain oils, the molecules are long chain hydrocarbons. Hard for them to slide past one another. Think about spaghetti, right? Spaghetti is a kind of pasta that's very viscous. You have spaghetti, the molecules get intertangled, and it's hard to pick up the spaghetti and move it from one place to another and get an individual spaghetti. If you had rigatoni or ziti or a different kind of cut, or elbow macaroni, they're easy to separate because even though the same mass of pasta, they're not long and skinny and intertwined and stuck on one another. So spaghetti is a great example of something that you would think of as being viscous, right? So let's read this notes here. The attractive forces, there are attractive forces between the molecules. There are usually structural features that exist that cause the molecules to become entangled like spaghetti. So we said for honey and sugars and syrup, it's these hydroxy groups all over the place. For oils and petroleum, it's the fact that the molecules are so long, right? They're so long that they become entangled. Like there could be molecules that are long chain hydrocarbons that are 8, 10, 12, 15 carbons long. So one of them is going to get intertangled with the other, and they're not going to be able to flow past one another. That's what viscosity is. In all cases, no exception to this, the viscosity of a substance goes down as the temperature goes up. Yeah, because as you give the molecules more kinetic energy, they are rotating, vibrating, and translating faster. There's more energy in them so that they can shake loose of those forces between the spaghetti molecules. Okay? So viscosity is very much a function of temperature. If you have an oil that's very, very cold, like in the wintertime, if you have to change the oil, you might want to heat the oil up before you put it in your engine. There are some large tractors and trailers, like diesel engines, where there's an electric motor to keep the oil warm so that it doesn't, clog up inside the engine and get too thick, right? You want the oil to work, so you might have to have an oil heater to keep your oil in your engine warm. Okay? And what's the reason for viscosity going down when the temperature goes up? It's because at higher temperatures, the greater average kinetic energy of the molecules more easily overcome the attractive forces between the molecules. Okay. Let's talk about adhesion forces versus cohesion forces when you think about a meniscus inside of a glass test tube or graduated cylinder. So here's two examples. So A and C are not multiple choice answers, A and C. They're A is for adhesion, C is for cohesion in these two cases. So what happens when you pour water into a glass vessel? Well, the attractive forces between the glass and the water molecules are stronger or better than the forces between water molecules and other water molecules. So given the opportunity for water to be touching glass or touching other water molecules, it would rather touch glass. So look what it does. It goes out of its way. It climbs up and defies gravity to a certain point. I want to touch the glass. I want to touch the glass. Now, it can't keep on doing that forever because the gravity would be so much that it would fall back down. But within reason, the meniscus is caused by the preferred attractive forces of adhesion beating out cohesion. Okay? If you had a substance where cohesion and adhesion were tied, it would be totally flat. Here's the test tube, and instead of it looking like this or this, it would just be straight across. It could care less. I would just as likely touch glass as I would touch another water molecule. That would be a tie. Okay? Well, there's a substance, and you've seen it, liquid mercury, is the opposite of water. Liquid mercury droplets, or individual mercury molecules, love to touch one another. And they go out of their way. They're so shy. They don't want to meet new people. They don't want to touch glass. So they pile up in the middle, to the point that if you've ever seen mercury on the floor, if there was a mercury spill, it would ball up into little beads of mercury. That's how much they want to defy gravity, that they're willing to make these tiny little balls, right, so that they don't have to touch the floor or the glass. So here's a case for mercury Hg liquid where cohesion, the forces between the mercury molecules, is greater than the forces of adhesion, the forces between the glass and the mercury. So two situations. Obviously the third situation would be a tie. So you can tell right away what is stronger, cohesion or adhesion, by what happens when you put the two materials together. Okay. These intermolecular forces affect properties of substances. So here's some of the properties they affect. Okay, they affect the viscosity, they affect the formation of a meniscus, which way it goes. Okay, and the last ones that there's two more that they're going to affect, and one of them is called surface tension. So surface tension is the energy required to increase the surface area of a liquid by 1 unit amount. So typically, they're going to be in joules per meter squared. So water at 20 degrees Celsius, pure water, has a surface tension of about 8 times 10 to the minus second joules per meter squared. That's the units. Okay? So if I was going to stretch water over a surface, how much energy would be caught up in that surface phenomenon called the surface tension? That's what it is for water. Other substances are going to have greater or lower numbers, but it's an energy unit per meter squared. Okay? All right, so let's talk about what causes this surface tension. So there's a couple of neat practical effects that you can see from this. One is that if you have a very light creature, like a very small bug, they can walk on the surface of water because they spread out their weight to such a point that it's not greater than the surface tension of the water. So they actually walk right on top of the water. Okay? If you have any, amount of mass to you, like a human being or something, this is going to be impossible. You'll break right through that tiny bit of force. But water has this little bit of tension, and you can see it. Another thing that some people are able to do if you have a very steady hand is you can take a paper clip and put it down on the surface of water so it floats on the water. Well, it's not actually floating. It's kind of resting on this surface tension of the water. Okay? So what causes this? That's kind of neat. Let's compare this situation over here that's unbalanced and this situation that's balanced. So within the bulk of the liquid water, once you get down a few layers, right, and here we only go down 3 layers. So these are the individual water molecules. Well, all of the cohesive forces between the water molecules are balanced out. So this guy in the middle has got 1, 2, 3, 4, 5 nearest neighbors around it in my picture. And the forces that it feels are equal for all 5, right? This guy up at the surface, though, has got downward pulling forces to this water molecule, to this water molecule, and to this water molecule. But it's not balanced by any upper forces of air up here. This air is basically naked, right? Air, the oxygen and hydrogen atoms are far apart. They're only randomly placed. They're nowhere near as close as they are in a liquid. A liquid is a condensed phase, like a solid, where the molecules are right on top of one another, like a crowded subway car. Here, this is freedom. They have no forces. So what's happening is you're kind of going to get pulled in or sucked in, and it's going to create this effect on the surface. And it kind of reminds me of like a suspension bridge where it's going to just kind of pull down and create this arcing situation that's going to hold the water on the surface together. So there's this extra forces, and these other guys would also feel it. I didn't draw it in. So it's this net inward force that's unbalanced that causes this tension on the surface, this pulling on the surface. And that surface allows you to do those weird things, like have put a paper clip on the top or have a bug walk on top. You can also take little teeny pieces of paper and like little confetti and put them down on the surface of the water. Before they get wet, they'll actually ride on the surface of the water for a while. Okay, so molecules in the interior are attracted equally in all directions. No net forces, where those at the surface experience a net inward force. The inward force pulls from the surface into the interior, thereby reducing the surface area. The inward force makes molecules at the surface packed closer together, causing the liquid to behave as if it had a skin. And sometimes it almost seems like it does have a skin. Okay. Another example, right? Besides viscosity, surface tension. And which other one did we do? Viscosity. We did the formation of a meniscus, surface tension. The last unusual property that occurs when the forces between adhesion and cohesion are out of balance, when there's a preference for one versus the other, is called capillary action. Now, capillary action is very important for plant growth. How does water essentially get pumped all the way up to the top of a tree and get to the leaves in a tree? Well, it's by this process called capillary action. So here's how it works. If you take a straw, okay, you put it into a liquid, since the adhesive forces are greater than the cohesive forces, you look inside the straw and you'll see a little meniscus, and you'll see that the level of the liquid inside the straw is greater than it is on the outside. Those water molecules want to touch that glass or that paper or that surface so much that they can defy gravity and get pulled up into it. Well, if you have thousands of these lined up next to one another, you pull it up and then pull it up a little more and pull it up a little more, and before you know it, you can use this as a mechanism to move water and pull the water up into trees by this capillary action. So the capillary action helps water and dissolved nutrients to move upward through plants. Okay, so intermolecular forces explaining liquid properties. So there are forces of attraction between molecules. The two that are going to fall under the bigger group called van der Waals forces are those super weak ones called London dispersion forces, and the stronger ones called dipole-dipole forces. So dipole-dipole forces are easy to explain. They're kind of like when the molecules have two poles, one side is positive, one side is negative, they act as little magnets. So they arrange themselves in a situation like this, where the positives are attracted to the negatives on other molecules, and that electrical interaction, which really what it is, when opposites attract, is going to hold the liquid together. So those are dipole-dipole forces. They are permanent dipoles, right? The molecule really has a positive side and a negative side all the time. So let's read this. Dipole-dipole forces result when polar molecules align themselves such that the positive end of one molecule is near the negative end of another. London dispersion forces are much, much weaker. They're just simply a weak attractive forces between molecules that result from small instantaneous dipoles that occur because of the varying position of the electrons during their motion about the nucleus. Okay, so let me try to explain it before we go into an example. So in a case, let me see if I can find something from the book that kind of shows this. Okay, so this is a figure from the book that's trying to talk about these very weak London dispersion forces. So you have molecules that don't have permanent dipoles. In fact, the example that we're taking is just picking the forces that would occur inside of atoms. So that's about as non-dipolar as you can be, right? You have the nucleus in the middle and the electrons are around the outside. But even atoms are going to have an attractive force for other atoms, right? They're not going to form a covalent bond, but they're going to be a little bit sticky to one another. So what would cause this atom to have a force with this other atom? Well, if you think about it, think about the nucleus as being fixed, right? So in any one situation, at one instant of time, this negative electron can be a little closer out this way versus this side. So that's going to cause this side of the molecule to be a little bit lopsided temporarily. So for a split second, this guy's going to have a negative over here. And then now this one is minding its own business. It's got one electron over here and one electron over here. Well, what's going to happen is that those two electrons are going to feel one another, right? And then this nucleus is going to have a little bit of attraction for those other electrons. And at that instant of time, they're going to hold each other together. Maybe these diagrams down here are a little easier to see. Let me see. So I have two helium atoms, no polarization. And then there's an instantaneous dipole. This guy all of a sudden shifts a little bit because the molecules are always moving. So if it shifts a little bit, and here's a little bigger, shifts a little bit, so then now the atom is lopsided and more of the negative side is over here than the positive side, and that's going to induce a dipole in the neighbor. So it's like a chain reaction. So this one, all of a sudden, this guy's minding his own business, and he sees that side so negative. What's going to happen over here? Well, what's going to happen over here is that side's going to be the positive side. This nucleus is going to be attracted to that negativeness, and for a split second, you're going to have an interaction. Now, a millionth of a second later, the whole situation could shift, where now this nucleus slides a little bit over that way, this side becomes positive, that'll make this negative shift over that way. So it's this constant shifting of the electron densities, so that at any instant, this one's positive, then this one's negative, then this one's positive, and this one's negative. And that tiny, tiny force between them is going to create this London dispersion forces. So in a sense, this is the weakest type of chemical interaction there is. These are just a few joules per mole. They're tiny next to our other forces, right? They're almost the force that you use when you don't have any other force to explain it, right? They're very hard to explain because they're so subtle. The other kinds of forces are easy to show. Ion dipole was easy to show. Dipole was easy to show you a picture of. Hydrogen bonds are going to be easy for me to show you a picture of. It's just these London dispersion forces, because you have nonpolar atoms or molecules, and all that's happening is there's a slight shift in the electron density that makes, for an instant, one side more positive than the other side, and it attracts the opposite effect in its neighbor, and that one attracts the opposite effect in its neighbor, and then that one attracts the opposite effect in its neighbor, and then all of a sudden you've got a little network of them holding together. Then a split second goes by and everything shifts. One atom shifts a little bit, and now it's slightly different, and its negative is pointing a different way. Well, guess what? It's going to cause a chain reaction of the 4 or 5 guys around it, and then it's going to be like, you go one way, then someone else goes the other way, like a whole bunch of people like dancing in a mosh pit, right, where you're kind of all on top of one another. One person makes a move, well, the other people have to adjust to it so that you don't crack heads, right? And somehow you all keep dancing really close together, but as one person changes the dynamic, the other people have to adjust in order for it to work. So you can't really pin down, okay, this is the negative side, this is the positive side of the atom or molecule. It's this ever-changing kind of tiny forces that hold the molecules together. Okay, so that's the best I can do. That's a hard one. You'd be much better off reading about it. Okay, let me go up to, we were up to page 17. Okay, now, one of the typical kinds of, so the overhead here is the diagram I just showed you from the book. So one of the typical kinds of examples that people would ask you is, what would happen to the following properties between these 3 kinds of molecules? Okay, so these are going to be 3 hydrocarbons. They all have the same molecular weight. I didn't draw the hydrogens, but out on the outside of every one of these lines, think of an H on there. So this is 5 carbons, okay, and then there would be 12 hydrogens around the outside. This one still has 5 hydrogens and 5 carbons and 12 hydrogens. It's just the way they're arranged. So these are 3 different isotopes of pentane. This one is called pentane, straight chain pentane. This is isopentane, where we pulled one off of the end and put it down on this second carbon. And this is called neopentane, which is the symmetric version. It looks like a little cross, right? You go 3 across this way and 3 across that way. So the 5 are arranged with 1 in the middle and 4 on the outside. But you still have 12 hydrogens here, 12 hydrogens here, and 12 hydrogens here. So over here I could actually write C5H12. And everybody realize I just didn't draw them because it would be hard to see all of the H's. But there are H's on all those spots around the outside. Okay, so none of these have particularly strong dipole interactions. The electronegativity of carbon is not that different than hydrogen. One side of this molecule is not much more positive than the other side. So what you have here, though, is the shape of them. Think especially about viscosity. The longest chain ones are going to be like spaghettis. So one spaghetti molecule and another spaghetti molecule are going to have a lot more surface area to interact and get stuck on one another. So my prediction would be that this one, the pentane, because it's the longest straight chain, it's not tight and in a small group, right? It's not compressed. It's got more surface area. This guy's got intermediate surface area. This guy's got the least surface area. This guy's really nice and tight and close together. Well, tight and close together is going to make it more volatile. It's not going to have as many places to be hitting other molecules. Let me try to draw that for you. All right, so here's the straight chain ones interacting with each other, touching one another. Look at all those places for them to get stuck on one another and for atoms to interact. Here's the middle guys, right? Not as many spots for them to get to because they're not as long as skinny. And the last ones are almost totally symmetric round. So the surface interaction is going to be the least. So the more branching you have, the smaller the forces. So the London forces, which are the only forces that can we have because to describe what the properties of the molecules would be. The London forces in pentane would be greater than in isopentane, then would be greater than neopentane. So if the forces are greater, what is that going to do to the amount of energy required to evaporate them? It's going to take the most energy to evaporate delta H of evaporation. How much energy does it take to evaporate it? Well, if these guys are all stuck together and have really tight forces and they're all holding each other together, it's going to be hard for one of them to escape and go into the liquid. It's going to have the highest delta H of vaporization. Isopentane is going to be in the middle, and neopentane is going to have the lowest. Well, if the vapor pressure goes in this direction, so does the boiling point, right? The guy with the highest boiling point is going to be pentane. It's harder to boil, to evaporate pentane. So the temperature at which you have to get to for the vapor pressure of pentane to reach 1 atmosphere of pressure is going to be higher for pentane than isopentane than for neopentane. So when we get to class, ask me questions about this. But this could be a typical multiple choice question where I draw 3 molecules and ask you, which would have the highest London dispersion forces? Which would have the highest delta H of evaporation? And which would have the highest boiling point? Okay, last topic for today is the ultimate in intermolecular forces. The champion of intermolecular forces. By far the strongest kind of intermolecular forces. And those are hydrogen bonded. Okay, so now hydrogen bonding occurs in molecules when the following situation occurs. They are the attractive forces that exist between the hydrogen atom that is covalently bound to a very electronegative atom. And there's only going to be 3 candidates. It's got to be fluorine, oxygen, or nitrogen. So whenever hydrogen is directly bound to fluorine, oxygen, or nitrogen, that molecule will have hydrogen bonds. And a lone pair of electrons on another small electronegative atom of a different molecule. Well, fluorine, oxygen, and nitrogen all have lone pairs of electrons. Nitrogen has 1 extra pair, 1 lone pair, it's got 2 dots on it. Oxygen has 2 lone pairs, and fluorine has 3 lone pairs. So here's the example of the hydrogen bond that would exist between hydrogen fluoride molecules. Now on the left here, this is one distinct HF molecule. This bond here is an intramolecular bond. It's a huge, strong bond between 2 atoms that are on the same molecule. So that guy is enormous. But in a liquid sample of HF, there's going to be another nearest neighbor. Right? Now I'm not saying that these hydrogen bonds that are going to form between this molecule and this molecule are anywhere near as strong as these covalent bonds inside the molecules. When you go to boil the HF, it's these bonds between this one and this one that's going to break apart. You're not strong enough to actually break the covalent bonds. All you're doing is boiling it. All you're doing is separating this to this. But, that being said, there is an interaction. Here's one distinct molecule. Here's another distinct molecule. Right? This is the negative side. This is the positive side. This is the negative side. This is the positive side. If we stopped right here, we'd call this dipole-dipole. But in this very special situation where hydrogen is covalently bound to fluorine, nitrogen over here, or oxygen, any of those 3 situations, you create a special interaction called the hydrogen bond. It is the intramolecular force between this atom and this atom, and that's what we call hydrogen bonding. Okay? Not that one or that one, but the interaction between the H on one molecule and the H and the F on the other molecule. So that's the example in hydrogen fluoride. Let me show you two more examples. Okay. Let's take a look at hydrogen bonding in water. Here's one distinct water molecule. Here's another distinct water molecule. Anywhere you see the dark line, see this one going up there? Another distinct water molecule. Another distinct water molecule. These are strong covalent bonds between the individual water molecules. When the water boils, what's going to break is those yellow interactions. Those are the hydrogen bonds. Hydrogen bonds can form between a hydrogen that's directly bound to an oxygen, nitrogen, or fluorine. So here hydrogen is directly bound to oxygen. And the lone pair on a neighboring molecule. So that's a hydrogen bond, that's a hydrogen bond, that's a hydrogen bond, that's a hydrogen bond, that's a hydrogen bond. That's the example for water. Water is a tiny molecule with a very low weight. Its atomic mass, its molecular mass is 18 grams per mole. Based only on mass, there's no way water should be a liquid at room temperature. Water should definitely be a gas. Oxygen and nitrogen are much heavier. Carbon dioxide is much heavier, and yet they're already evaporated. They're already in the gas phase. They can't hold themselves down. But water holds itself down in a glass of water, in the ocean, in lakes. How come? Because of these hydrogen bonds. All right, last terrific example. We already did the HF one down here, so let's finish up with ammonia. Anytime that hydrogen is directly bound to either oxygen, nitrogen, or fluorine. Now there are other molecules, but these are the champion examples. Okay, so ammonia is NH3, and they make these little pyramids. The nitrogen only has one lone pair, but it only takes one. This is a distinct ammonia molecule. Here's a distinct ammonia molecule. Here's a distinct ammonia molecule. Here's a distinct ammonia molecule. How come ammonia will stay down as a liquid when its molar mass is 17 grams per mole, even lighter than water? Well, the reason is because of the strong interaction between the H on this ammonia and the lone pair, there they are, those two dots, on the other ammonia. So when ammonia boils, it's the yellows that boil away. I should make this guy yellow too. Right. And here's our example of HF. So hydrogen bonding is like the Superman of dipole-dipole interactions. Okay. Almost done. Then we're going to go, chapter 12 starts solid, so I'm going to stop right there. The last example of ion-dipole forces are the attraction between ions and polar molecules in solution. I can find you a nice picture of that from the textbook. These are very easy to understand. Something like you take salt water, and you take the salt and dissolve it up in water. Let me see if I can get a nice graphic for that. Here's a perfect one. This is on page 444 of your book. Right? Look at that. These are individual water molecules surrounding the chloride ion. So that negatively charged ion, this is a permanent Cl minus, right? It has one extra electron. So why does salt dissolve in water so well? Because the salt gets hydrated by these 6 water molecules. And who's pointing in? It's the H that's interacting with the chlorine. Why? Because the H is the positive side. This negative O, right? Because the water molecule is very polar, right? This negative part of the molecule is pointing away from it. So that's how you solvate the chloride ion. This interaction would be called an ion dipole. The ion is chloride ion. The dipoles are water molecules. Okay, when you take salt, salt doesn't just have chlorine in it, it also has sodium. How is the sodium hydrated? Well, in salt water, 6 water molecules also do the job of solvating the sodium ion. That positively charged sodium ion is surrounded by 6 water molecules. Who's pointing in this time? Not the white hydrogens, but the red oxygens, which is the negative part of the molecule. Not a big fat -1, just a part of a charge. But 6 times a little bit is a lot. Reminds me of Gulliver's Travels. You know, you can tie Gulliver down with 50 gazillion ropes. Well, that's what we're doing. We're just getting them little tiny forces, but you got enough of them, and you can dissolve them. So when you think of salt dissolved in water, think of the NAs separated from the chlorines. Okay, they can't get back together because these guys are surrounded by waters, and these guys are surrounded by waters. Almost like it's posse, you know, or its followers always staying around them. Never really get that close to each other. Always solvated. You have to boil all the water away to get the Na back to the chloride ion. Okay, so that's our last example. We're going to pick up on page 19 of these notes. That's everything for chapter 11. Next thing I'm going to talk about is chapter 12, which is going to start with metallic bonding. And chapter 12 is dedicated to solids. Thanks.